Hi there, welcome back. This is part 2 for our lesson on optimization. Make sure you watch the first video before watching this one. Let's get started with some more problems. As you may remember, in the first video we ended with some two-dimensional optimization problems. So now we're taking that to 3 dimensions. So basically that means rather than looking at shapes that are two-dimensional, we're going to look at 3D shapes. Let's begin with this one. We have an open box with a square base and a surface area of 192 square centimeters. And we are trying to maximize its volume. All right, so this picture is not very good, but imagine it's a box with an open top, so there's no surface there. Okay, let's begin like we did with the other optimization problems. Usually we have enough information to make 2 equations. So let's make an equation for volume and another one for surface area. Try that now. Okay, here's a volume equation. We know volume of any prism is base area times height. We know this is a square-based box, so the base has an area of x times x, which is x squared, multiplied by the height here, and we have a volume of x squared times h. Base area times height. Great. Surface area looks like this. We are told that the surface area is 192, so we put that here, and we know this box is made of 5 surfaces. The bottom, and then the 4 sides. The bottom has an area of x squared, so that's here. And then plus 4 sides, and each side has an area of x times h, because those are 4 identical rectangles along the sides. So there's our 2 equations. And as you remember, with optimization problems, now you have to look at the 2 equations and decide, well, which is the one I'm trying to optimize? Which is the one I need a max or min point for? And we can see here that we are trying to maximize the volume. Therefore, we will focus on this formula, or this equation. And in this equation, we have 3 variables, so we want to bring it down to 2 variables, because we cannot take the derivative if we have 3 like this. So let's use the second equation and substitute for something here. And I will suggest you solve this equation for h, because that's easier to solve for. And then take what you find for h and put it in this volume equation, and then simplify it. Let's see if you can get the correct volume equation in terms of x. All right, so solving this for h, we get this. I did 192 minus this, and then, all right, now that we have that h value, we're going to substitute into the volume equation. So there it is, that h has been replaced with this h here. And now simplifying that further, we can multiply by x squared along the top of this fraction to get this. Notice we have x squared here, and then x squared times x squared is x to the 4th here. And finally, you can actually, I would suggest we split this into 2 fractions and simplify. So if you do 192x squared divided by this, we actually get 48x. And if we do negative x to the 4th over that, we get 1/4, which is our fraction, and then x to the 4th divided by x is x cubed. You could have written that with the x cubed on top, but I put it like this because it's easier to take the derivative when we have this coefficient in front. Okay, double check everything, make sure you're confident about that. Now, we know when we're trying to maximize or minimize, we can find the point where this function has either a max or min point, which means it'll have no slope. So let's take the derivative and set it equal to 0 and solve for x. Okay, and here's what we get when we do that. So here's the derivative of that. Check your work. Set it equal to 0, because again, when we find max or min points, that's when there is no slope. So we're setting the slope equal to 0. Solve that for x, and you get plus or minus 8. The feasible solution is 8. We ignore x equals negative 8 because we cannot have a negative dimension on this box here. All right, so now that we have x equals 8, we can find the maximum volume. But let's confirm first that x equals 8 is actually a value that maximizes the volume. So if you put, okay, I don't have it on there. There's 8 on there. If we put a value before 8, anything less than 8, into our derivative here, we get a positive value. If we take a value greater than 8, any value greater than 8, put it into our derivative, we get a negative answer. That tells us the function is increasing and then decreasing. So that confirms that when x equals 8, we have a maximum point. So we have found a maximum volume. And that maximum volume you can also calculate by putting your value of 8 into your original volume formula here, for example. So what is the maximum volume? Great. The maximum volume, does it have it here? No, we found the base is 8 by 8, the height is 4, and I don't think I even have the maximum volume there. All right, let's try this next one here. Read the problem. Okay, so what we are trying to find here is we have a can, a cylindrical can, and it has a standard volume of 330 milliliters. That's a normal can size. Companies are interested in minimizing costs of production in order to maximize profit. So they want to use as little of the material for the surface area as possible, but maintain the same volume, right? So what is the minimum amount of aluminum they can use? So we are trying to minimize the surface area this time. Let's begin by reminding ourselves what the formulas for volume and surface area of a cylinder are. So here's a cylinder. The volume is pi r squared times h. That means base area, which is a circle, pi r squared, times h, the height. And that's how we find volume of anything, base area times height. Okay, surface area is 2 pi r squared because the surface here has two circles, so 2 pi r squared, and then plus the surface area of the lateral surface, which is what we wrap around here, and that is given by 2 pi r h. Okay, reminding ourselves what those are, we can continue. So their goal is to minimize surface area. So find a way to combine the two equations to create an equation for surface area in terms of the radius r. So see if you can write both equations and then combine them in a way so that you have a surface area equation that has only r as one of the variables on the right side. Okay, let's try. So here's our volume. Here's the surface area formula, which we're given to you already. Now, you can take this one, and we know we're trying to keep the volume at 330 milliliters, so we replace volume there. Now, this one can be solved for h or r, but we were told we're trying to create this equation in terms of r. That means you want r to remain, but you want the h to disappear. So let's solve this for h. That equation solved for h is this. Now that can substitute back in here. So there's that substitution made. That h is replaced by that. And now we have an equation for surface area in terms of r, the radius, only. Of course, this can be simplified further. We get this. So notice here, if we multiply here, the pi here cancels with this pi. This r and this r cancel each other, so we're left with just 1r here, and 2 times 330 is this. So now we have an area model that is in terms of r only, and that area model is only for cans that will have a volume of 330 because that substitution was made. All right, so let's maximize. No, we don't want to maximize this area. We want to minimize it because we want the minimum cost for this company. We want them to create a can that has a minimum surface area. In other words, a minimum amount of aluminum or tin they have to use. Okay, so let's do that. We already found that. Yeah, minimize it. Let's try. So here's our area formula. We're going to take the derivative when we're minimizing. We take the derivative so we can find out when the slope is 0. Set that equal to 0 and solve that for r. What do you get? Okay, I multiplied everything by r squared to begin. And now I'm solving this. Take a cube root on both sides here, and we find out r is 3.74. Okay, that is the r value that gives us either a max or min point for surface area. We can confirm that is a max or min, but we'll do that in a second. Let's plug that r value in here in the area formula, and we get an area of 264.4. That's our minimum surface area. So now that we know r is 3.74, we can also find the height. Let's find the height. Okay, plug that in there, substitute in, we get a height of 7.49. Notice that your height and your radius are not too far off of each other. What that tells you, actually if you doubled this radius, you would get a diameter which is nearly the same or is the same as this height, which is odd. Can you imagine a can where the diameter of the circle on the bottom is the same as the height of it? That's not really what happens with these cans, right? If I go back to the image of the can, definitely the diameter across the bottom here is not the same as the height. So a company doesn't always choose to minimize the surface area. They don't mind the extra costs of this extra material, because what happens when you have a taller can is basically it's more visible to the customer. So it turns out maybe it's even better that way. They can make more money and not save money on the can itself. All right, so try another one. Read this problem here, and let's begin by, well, let's pause and read it first. Okay, now that you've read it, let's begin by looking at this box and saying, okay, if you cut these corners out like it says, these 4 corners, and then you fold up these sides, so I hope you can visualize how that would make this box, but what are the dimensions? How long is the longer side of this box? Right here. Well, that must be 24 minus 2x. The reason is because we have the longer side here, and the length here is the length from here to here, which is the entire length of 24 minus x and minus x again. It's 24 minus 2x. Okay, with that in mind, how long is this shorter side right here? Well, I hope you came up with 15 minus 2x, because 15 is the entire length, and again, we're subtracting x, and then this length must be 15 minus 2x. Great, how tall is this box? That box has a height of x, because when you fold these up, that height there is the equivalent of one of these, x. All right, so now what is the volume of that box? Or actually, try the whole thing. We're trying to maximize the volume. You want to maximize the volume. So what will be the x value, the amount you cut off here, in order to maximize this volume? Let's see if you can figure it out. Okay, volume is given by this times this times this, so there's the volume. We get this volume equation. We take the derivative of that volume to get this. And then we're going to maximize the volume. So we're going to find the max or min point, set that derivative equal to 0. That work is here. And by the way, that equation here is a quadratic which can be factored, and it can be factored into what we see here. Set that equal to 0, and you get 2 answers, 10 and 3. So now you don't know which one, 10 or 3, which one is the one that's going to actually maximize. One will be max, one will be min. But 10 is not within the domain. What that means is we cannot have an x value of 10 here. If you made that 10, then it would be 15 minus 10, which doesn't work. So right away we can eliminate 10 and say 3 is our only possibility. And notice that here they took a different approach. You could take 3 and test it in the derivative to see if 3 is a max or min. But if you may remember, we also had something called the second derivative test, and that's what we're applying here. We are finding the second derivative, so we took the first derivative, took it a step further, found the second derivative, and then put the possible max or min point into the second derivative. So right into here we put 3, and that gave us a negative value. And what that tells us, if you remember, the second derivative test tells us when a function is either concave up or concave down. So this function, by seeing a negative second derivative value, we know at x equals 3 it is concave down. And if something is concave down, it means that point must be a maximum point. So that's what we concluded here. And you could have used the first derivative test to also double check that, and you would have found the function is increasing before x equals 3 and then decreasing, which also tells us it's a maximum point. All right, so then the volume, you put 3 back in the original function, and you find out that that maximum volume is 486 centimeters cubed. Great job if you're able to solve that all the way through yourself. Let's end with one last problem, but before that, check it out. Here's a graph of our original function, and that graph confirms what we're seeing, that at an x value of 3, we have a maximum volume of 486, and that's what we see here. So that graph can always be used to check our work and confirm. All right, try this last one here. So pause, or actually the video will pause for you. Read this problem and see if you can figure out a number of workers that the company needs in order to produce a maximum 1,200 fishing poles. All right, so revenue is given here, we're given costs here, and we're trying to maximize profit. So take a look at this and let's solve it step by step. All right, and that's a tough problem. There's a lot going on there. So how about you check your work here? Pause here, check how you did, and we will see you in the next lesson to try more problems like this together. Great job. See you next time.